Okay, so this is the first part of the Mod 1 Part 2 slides. I'm not quite sure how many parts are going to be because it's going to depend on how long it takes to go through them. So, Part 1 talked about what we call one sample hypothesis test. And this is where you have a population and you pull a sample and you're just looking at the sample mean and how it compares to a hypothesized value for the population mean. Okay. There's two issues that I kind of sort of ignored in the first set of slides that I want to talk about briefly. Um, the test we did in part one is the null hypothesis of the mean being equal versus the alternative of the mean not being equal. Now, you can actually do a test where your null is always going to be equal to, but you can also do these what we call one-sided tests, where you're testing for the mean being greater than or less than. I hate these. Okay. There's a reason I hate these. It's not just random. I hate these because um what the test here is going to pick up is only if it's greater than, so it's only going to pick up like something out here. And you can actually have a case where it's significantly less than and it won't pick that up. So I don't like these because they don't pick up specific, like they only pick up one direction, whereas this one picks up whether it's bigger or smaller than the hypothesized mean, whereas this would only pick up bigger, and if it were significantly smaller, it would just like not get picked up by that test. I don't like these cited tests. That's just my personal bias. I don't like them in practice. They are used a little. We're going to see a better case of a citedness when we talk about a paired t-test for two samples. So I just want you to be aware that you can do these tests. In the interest of time, I'm not going to elaborate too much more on that. The other issue is levels other than 95%. This is actually really easy to deal with because you're going to get a p-value. And so if you learn to read p-values, if you got a p-value, for example, of 0.02, that's an interesting one. Okay. So at the 95% level, you're looking for a p-value less than 0.05. But at the 99% level, you're going to be looking for a p-value less than 0.01 because effectively 95% is using the critical region where 5% of the curve is extreme. So that's your p-value less than 0.05. It means that your critical value, or your test statistic rather, is in these regions. The critical value is the marker value of the distribution. The test statistic is what comes from your data. But your test statistic is in here. Your p-value is less than 0.05 at the 95% level. If you're doing this at the 99% level, all that means is that you're moving your critical value and what we also call the critical region, which is the red region, a little bit further out. So with the standard normal, this is 1.96. I don't remember exactly what it is for 99%, but you're going to have to look for a p-value less than 0.01 to be significant in this case. Now, if you get a p-value of 0.02, this is an interesting case because this would be significant at the 95% level. However, if you were going to the 99% level, it would not be significant because 0.02 is not less than 0.01. Typically 95, 99, you could also do a 90% test, which honestly, I've hardly ever seen 90% test done. And in that case, you'd be looking for a p-value less than 0.1. So you don't really have to worry about like a different test for testing at another level. This, if you're using a p-value, which you are because you get one in the SPSS output, you just look at whether your p-value is less than 0.05 for 95%, less than 0.01 for 99%, and less than 0.1 for 90%. And that's really all you have to do. Again, I'm going to heavily emphasize the 95% because I don't want people to get too distracted by like the different level test. You may, for some reason, want to do a 99% test, or, honestly, I have literally dozens and dozens of professional publications and stats. I've never seen a 90% test done. 99, I think, would be possible in some stringent, like, medical applications and things where you know. There's also a trade-off, again, between making errors at different levels. So that's the interpretation of that, and that's all I want to do on that. because there are some questions in your problem set that might ask about like and this also is alpha. Alpha's level. So this is alpha's 0.01, this is alpha 0.05. That's what alpha means. I'm not quite sure why, and then this is like alpha over 2 is like the region. So when you see like Z alpha over 2, it's referring to alpha being 5%, and then these would be the standard normal scores that are like in the extreme. Alpha over 2 would be 2.5% here and here. That's what that means. I don't, I've been in stats for a long time and I don't entirely understand what the need for the alpha in addition to everything else is, but yeah. Anyway, so that's the one sample test, and that for now is done. The one sample tests are slightly, I find them easier and harder because they're more simplistic statistically, but they're conceptually testing against like a hypothesized mean is a little bit of a strange thing to do. These are actually used a lot also, by the way, in like statistical testing. Like when we do correlation regression next, we're actually using a one sample test to test if a correlation is equal to 0 or not. So these have like sort of like theoretical statistical applications in addition to practical applications. Okay. So enough about one sample test. Let's talk about two sample tests. What exactly is two samples? Two samples are a little trickier, a little more complicated, and there's multiple situations. I think my power is dying out, so the old lady has to put her little thing back in. Anyways, so two sample tests are not, now it's not like you're just resampling. So we have a population, okay, and we take a sample, okay, and it's not just resampling and taking another sample. No. This is like the kind of thing you do when you're doing like the central limit theorem, getting multiple samples. No. So a two sample test, what it is, there's two versions of it. The easier one is like it's kind of stratified. So this would be like men, and then you sample women. Okay. So you're sampling like two distinct groups from a population, and here we have two samples because they're going to be men are one group and women, females are another group. So you have a sample of men and a sample of women, and you're going to be comparing the means for the two different groups. Okay. This would be a two sample test. And in a two sample test, you're comparing means not to a reference value like you were in a one sample test, but you're comparing the two means of the two groups or two samples. Okay. That's one version of a two sample test. This is the one that we call independent samples. We're going to study both of these, like this whole presentation is about those. So the independent samples means that you're sampling from a population. It's basically you're looking at two different strata, whether it could be treatment patients and control patients. It could be different groups. For this test, we're going to talk about two groups. Later on, coming up, we're going to talk about multiple groups. So for now, we're just going to consider sampling two samples, but we could actually do this with multiple groups. That becomes the analysis of variance that expands on this. So that's another kind of test that's in mod 4. So a two sample test of independent groups compares the two different groups. So we're comparing the two means. We're not comparing a mean to a reference value like we were in a one sample test. Okay. That's this test. The second test is a dependent sample test. And you're like, what is that? So these are both two sample tests, but there are two pretty different types. The first one is this comparing the mean of two populations or two like strata within a population. That would be two independent samples. The second test is what we call dependent samples. And you're like, what is that all about? Dependent samples, you're always sampling a population, but a dependent sample is something like before and after. So you're actually sampling from the same population essentially twice, but you actually are doing the same individuals. So the same subjects are sampled before and after. This is not the same thing as this because in this case, the two groups are independent. Like the same person isn't going to be in both groups. This, it's kind of quasi two groups, but it is considered a two sample test. This is going to be the same individual, but before and after, so it's two different time frames. This is what we call dependent. And typically before and after is in fact the case that's used with it. So you can't consider these as independent because it's the same individual, and when you have the same individual, it's going to be correlated, and there's issues with So these are not considered independent, but this is the second type of two sample test. Um, Typically it's before and after, or like it's something of that sort. These are also occasionally done in what's called matched pairs, which used to be like identical twin studies. Those are not as common as they once were, but that is another type of situation this might occur. So these are the two types of comparing two means. Okay. Um, in both methods, we're going to be doing a means comparison. It's just in this method, we're comparing two independent groups, like the mean of group A versus the mean of group B. Okay. And in this method, we're doing basically a before and after. So the mean before compared to the mean after. Okay. This also, I keep meaning to modify the curriculum of this course. Eventually I will, but there's so much stuff already. This becomes also, if you expand on it, it can become repeated measures we're doing before, after, and like time 1, time 2, time 3, time 4. That would be important, like if you're doing therapeutic treatment and you're sort of like monitoring how things are going at different time intervals. The methodology from the dependent samples would carry over into that. This is a little more complicated for this course, but this business of, measuring a baseline of before and then after treatment. For the two samples, we're only interested before and after, but we could expand on that and do like time 1, time 2, time 3. So those are the two contextual situations this occurs. Now, these tests are actually, they are statistically different, so we're going to study each of them, and that's basically what the rest of this presentation is going to be, no matter how many parts it is. I don't know yet. I'm doing it as I go. Okay. So the first one we're going to study is the independent samples. Okay. Again, if you read the textbook by Blumen, they make this big to do about known and unknown population standardizations. SPSS couldn't care less. There's no difference in the known and unknown population standardization. So it's just one test. And the test is you're comparing two groups. So you're taking samples, it's basically stratified sampling. You're taking group A and group B, and you're comparing the average of group A to the average of group B to see if there is a difference between the groups. This is actually, by the way, it's a really easy test. When I teach stats 1, I actually teach this before I teach one samples, because the context, this is a really commonly used test and it's really easy to understand. So the null hypothesis is always this. It doesn't matter. The null hypothesis is always that the group means are equal. So group 1, whatever the mean is, group 1 is equal to group 2 in terms of its mean. Okay. That's always the null hypothesis. So there's nothing, it's not like the one sample where you're like comparing it to a mean of some value. You're just comparing whether or not the two means are equal. And likewise, the alternative hypothesis is that the two means are not equal. Now, an alternative way to write it is to do subtraction. This just means that like if you had mu1, mean 1 equals mean 2, and then you subtracted, like you can write it this way, and then it's equal to 0 or not equal to 0. It's exactly the same thing. I like this way better, but this way is equally logical. Okay. Technically, you could do like a greater than less than, but we're not going to go there because that's not a super practical thing to do anyways. Okay. So this is the test of independent samples to compare two means. Okay. The test statistic, and you don't really like, this is to look at because I do want to, all of our test statistics look like this. We're measuring how far our observed value is from our expected value divided by the standard error. Now, in this case, the observed value is the difference of means, and the expected value is this. This, of course, is actually to be 0. So we're basically testing whether or not the difference of means is 0. Okay. Because your null hypothesis is that the difference of means is 0, and we're testing whether or not the two groups have no difference or a difference. No difference would be 0. A difference would be something other than 0, whether it's less than or greater than, doesn't really matter. And then when you calculate the standard error, you're actually pooling. This is the standardization of group 1, the standardization of group 2, the sample size of group 1 and group 2. The groups do not have to be equal. Like you don't have to have 10 and 10. They shouldn't be grotesquely asymmetric. Like you don't have one group with like 600 people and another group with like 4, but there's no requirement that they be equal because that's actually accounted for here. Okay. And then so what we're testing is the distribution of the differences being 0. Okay. So this is essentially the null hypothesis rewritten as a normal distribution. And if the null hypothesis is correct, the two means are equal or the difference is zero. And so that would mean that the mean difference is zero, and we're testing whether or not our sample means from the two groups are equivalent, whether the difference between the sample means can be considered part of a distribution where the mean is zero. Okay. So that's what's being tested. Okay. SPSS computes the test statistic for us. In the old days, you could do that by hand, but I mean, there's no tremendous value in doing that other than people might make mathematical errors. I don't love textbook problems because in the real statistics world, you don't really have problems that you can actually do with paper and pencil unless you're working with minuscule samples. And if you're working with a minuscule sample, you're probably going to use non-parametrics and not this anyways. Again, the sample sizes do not have to be equal. They shouldn't be crazy different. Now, the standard deviations, we're actually going to see these should be at least kind of equal. They don't have to be exactly equal. There's actually something called Levene's test. And SPSS is going to give us this. The only time there's an issue is if these are like egregiously off. Now this is a variance, not the standard deviation, but if I take that. But so if I look at the standard deviation of group 1, the standard deviation of group 2, they should be pretty close. Levene's test, we're going to see this in the SPSS output. So there's actually going to be a test for whether or not they're like totally different. And that would be a case where like here's group 1 and like here's group 2, and like the variability is like way bigger here than here, which you could see in a normal distribution. That because remember, these are sample means, so they always come from normal distributions, but like this one would be peaked and not very variable, and this one would be, then you kind of have a problem. But SPSS actually gives an alternative output to account for if this happens, so we're going to see this. So yeah, so it's only an issue if there's like a really big difference in the variability of the groups, then you want to consider that. Everything else becomes basically the same as the one sample test, except that in this case, you're using this. I don't know what this is doing. You're using this as a test statistic. This is going to be calculated by SPSS. No one has to do this by hand anymore. Not at this level class. In Stats 1, they might make you, but not here. Okay. So again, like the theme of doing a test is consistent. Okay. Very, very consistent, our theme of doing a test. Make a claim. Okay. So the claim in this case is that the means are equal. That's always the null hypothesis. Collect the data, get the mean from group 1, get the mean from group 2. You're also going to have the sample size and the standard deviations. Those get plugged into this formula, not by us, by SPSS. This right here is a difference that's going to be 0. That's what we're testing against. The test statistic gets computed from the data, and then a decision is made based on the test statistic, and SPSS is going to give us this in a p-value. And then we make a conclusion whether or not the means are equal or not based on the test statistic and its associated p-value. Same process, because you're going to see quite a few different tests, and they're all going to be similar in that respect. Okay, so this there is a method. I know I said in the introduction to hypothesis testing that there's 3 methods of looking at hypothesis test. One is the p-value. The other one is to look at the test statistic. P-value and test statistic are redundant. P-value is area associated with test statistic. They're just 2 ways of looking at the same time. The third thing to do is look at confidence intervals, which for the 1 sample test I didn't care about. For the 2 sample tests, and this formula here is somewhat of a nightmare, but it's really not all that bad. Because this, believe it or not, is a point estimate plus or minus a margin of error calculation. Again, this is the point estimate. It's just that in this case, it's the difference of means. This is the margin of error. The formula is kind of similar to that for the test statistic and accounts for the variability in the sample size and the critical value. Why would this matter? We're going to see on the SPSS output, it's going to give us these confidence intervals. Now, this is not a confidence interval for mean, though. The difference in this case is this is actually for the difference of means. If this includes 0, if 0 is in this interval, then we have a non-significant test. Okay. And it's sort of a redundant way of the same outcome. If 0 is in the interval, it means that it's likely that there's no difference between the means and that they come from this population. So a significant test with a p-value less than 0.05 is not going to have 0. But if we have a 0 in this interval, it means that the difference of means is really not that much off from 0. And we're going to actually see this in the output. We don't really super need this. If we have the p-value, that's really all we need. This is like added detail. It's in the SPSS output. It's just redundantly stating the results of a test in terms of a confidence interval. So we're going to see this. Okay. I don't know how long my video went, so I might actually, well, let's actually, I don't want to split things up too much because that will make everybody crazy, including me. I can't figure out what this is doing. Okay. So, well, let's actually go over this, and then I have a feeling I'm gonna go into SPSS. Now, this is the egg data that I talked about a little bit before. This is a data set I made up a couple years ago, one of the first couple times I taught this course, like 4 years ago or so. And I just collected data on different kinds of eggs, including organic, non-organic, brown, and white. And I actually did it like intentionally, like because it was a great way to illustrate different hypothesis tests of means. So this is looking at brown versus white eggs. I'll show you this in SPS in a minute. But the null hypothesis, now these are two like different groups. So brown versus white eggs are like two groups to compare, which is good. And the null hypothesis is that the brown eggs are equal to the white eggs. So this is like brown equals white. And then I write it in terms of the mean difference equals 0. That's what we're testing against. Is there no difference between brown eggs and white eggs? Okay. The alternative would be that there is a difference. Okay. This is the independent test. We haven't talked about the dependent test yet. Okay. So that's what we're going to test. And again, so the claim is that the brown eggs is equal to the white eggs. Then I collect the data. We get all kinds of little metrics from that, including all of our basic statistics. SPSS calculates a test statistic for us. The test statistic and its associated p-value determine the results of a test. And SPSS is also going to give us the confidence interval output for this, but that's not 100% necessary, but it's there and it's nice to know how to interpret it. Okay. So when we go in SPSS, I'm not yet, but I'm going to talk about what this is. So there were 40 samples of eggs, and the mean price of brown eggs, they're all for a dozen, was $4, and for white eggs was $2.64. So they look pretty different. I don't know why. This is not accounting for organic and inorganic, but brown eggs appear to cost more than white eggs based on this data, but is that a significant difference? And the answer is you can't really tell by just looking at this. Now, the standard deviations are not super far off, so we're not going to have an issue like where these are like too crazy different. That's I erased it, but that's this issue here, which we're actually going to see Levine's test. We want for the two groups to have relatively consistent variability. That's not like they don't have to be equal. You can't have a situation where they're just completely and totally like one's way more variable than another. That's a problem and it gets corrected in SPSS. So yeah. And then so SPSS is going to run the test and it's going to give us a test statistic and a p-value, and based on that we then interpret it. Now just looking at the metrics, I mean it looks like this is going to be different, but you can't really just look at it. You really need to actually run the statistical test. If we could just look at things and make the determination looking at them, that's not really statistics. That's just describing, I mean it's descriptive stats, but that's not inferential testing. It's not going to the level of actually like showing something at the level of performing a formal hypothesis test. So yes, looking at the descriptive data, the means do look different. The standard deviations are fairly consistent. The sample sizes are not consistent. That's, again, it's not a problem when you run this kind of test. You shouldn't have like 401 and 10 another, but 26 and 14 is fine. So SPSS, we could basically, we could fairly easily do this one by hand. In fact, algebraically, you could just stick the numbers in, right? X1 minus X2 would be like 4 minus 2.64. That's these guys. Like you could just call this X bar 1, X bar 2. minus 0, and then you could just stick all the numbers in. I'm not going to finish that because I just don't feel like it. But I mean, you could do like 1.32 squared over like 26. And if you did that and fiddle with this, you should be able to, as an exercise, match SPSS's output. But I have a feeling nobody's going to actually do that. But algebraically, you have the skills to do that if you wish. Okay. So when I run this in SPSS, which I'm gonna do the second video and show that there. The test statistic turns out to be 3.336. Now again, our knowledge of the normal distribution, 1.96 is our cutoff. This is gonna be a T, not a normal, but it's gonna be pretty darn close. So like having a test statistic of like 3, it's pretty certain that it's gonna be out here in the critical region. And the associated p-value from SPSS is 0.02. I don't know if there was more digits to that. Okay. And so based on this, we would conclude that there is a significant difference between the groups. And we reject the null hypothesis that there's no difference. Because remember, the null hypothesis in this case is that the groups are equal. The alpha is 0.05 because that's a 95% level. Alpha is just, if we're doing a 95% test, it's just 1 minus that. If we're doing a 99% test, then alpha is 0.01. But the p-value is less than 0.05, so we would conclude that there is a difference, and rejecting the null, that there's no difference. Okay. However, again, in this case, if we were running a 99% level, we would actually like change it to fail to reject. Now, ethically and morally, if you want one result or another, you could technically change the test level and you get like a fail to reject versus a reject. That's not the greatest practice in the world, but in a case like this, you kind of like could look at it either way. Okay. So that was brown versus white. I'm going to actually break because I have a feeling this video is getting a little bit long. And then I'm going to do another video, doing the one we just looked at in SPSS and also running the organic versus regular in SPSS. So that will be part 2.